Yeah. So it's probably you can hit the back.
Oh, wait a minute.
It's got
Okay. Yeah, so thanks for coming here early in the morning. I'm Sujay Sangvi from UT, and I'll be talking about understanding contrastive learning via Gaussian mixture models. This, my two co-authors, I think they're in the audience. Parikshit is a student at UT, Ali is a postdoc at UT. They were here yesterday as well. In the abstract, I had also mentioned that I'll be talking about understanding model retraining using its own outputs with Rudrajit Das, who, as per his website, is just another guy working in on a PhD in machine learning. Though I think that's soon coming to an end. The fact that he's doing his PhD, I mean, he's graduating soon. I will. As I was making talk, I realized I won't have time to talk about this, but Rudrajit is here, I'm here, and we're happy to chat about this as well. So I'll only be talking about understanding contrastive learning for Gaussian mixture models. And I don't have too many slides. The flight was only 3 hours. And so, just feel free to stop me at any time if you have any questions. I think of this as like preliminary work. And I think there are a lot of like interesting questions which I want to answer. Okay, so just a brief primer. I think many of you might already be familiar, but for those who are not, on what is contrastive learning. So what contrastive learning is an unsupervised way to learn representations, right? And it's built on a simple idea, which is that, unsupervised means there are no labels for points, right? So it's built on a simple idea, which is that you have pairs of points and you try to learn representations so that for every point, for every point you're given a partner, right? And you'll use these partners to learn representations. And the way you'll do it is you'll try to make a loss function which encourages the representation of a point and its partner to be close by, and the representation of a point and a random other point to be far apart. Right? So that's why it's called a contrastive. You kind of want to contrast the distance to your partner, and you want to be far from everybody else. Okay. It's become a pretty common recent theme. So for example, before I go further, can anybody name a foundational image encoder? What's a foundation image encoder everybody uses? Clip. Yeah. Okay. So clip is an example of this, right? And so that's an example of a pretty common recent theme, which is to train very large models on a very large corpus of data using unsupervised, in an unsupervised way. And specifically also pretty popular is using that unsupervised way is contrastive, right? Like, except for, I guess, next token prediction in language, I would argue contrastive training is the most popular, like, unsupervised way to train big models. Okay. And so once you do that, then you can fine tune or further train or adapt this model to a downstream task, right? So you can take a clip encoder and, specialize it for ImageNet 1K or ImageNet 21K classification. And that often beats anything else you can do for that data set. And so it's a simple idea that works zero shot, even with no knowledge of the downstream task. So this is, this is what contrastive learning is. So I'll just give 3 examples. They're all super popular. They have like thousands of citations. So the first one, I'm sure almost all of you have heard about them. So the first one is SimClear or SimCLR. What that does is it's only for images. It was proposed for images. right? In this paper, I think there have been, of course, extensions. So what this does is, so remember, what do we need? We need a point and we need a partner. Where do you get a partner, right? If you just have a bunch of images, where do you get a partner? So the idea is that they want to keep images to be semantically similar to their partners. And so they say, okay, one way to get a partner is to take a mirror image, to take a mirror image of your original image, or to crop it, or to translate it, and so on. So you have like a whole bunch of like augmentations. And so you get all these pairs, right? And so you have an image and you augment them. And then, so you get a pair. And then you take another image and maybe one of its augmentations, whatever, right? And then the loss will try to make the embedding of the pairs to be close by and the embedding of this one to be far away. That's it. Right? So you learn some ResNet body, like the trunk without the prediction head, so that the final embeddings satisfy this kind of similarity. Does this seem clear? Another example is a dense passage retrieval from, I think, 2020, right? Which, I would think of it as quote unquote multimodal, even though they're both text. So this was trained on, kind of a they took pre-trained BERT and then further fine-tuned it for question answering using this contrastive loss, where you have a question encoder on one side and a passage encoder on the other side, and you again have these random negatives. So the pair is the question answer pair, so it's already given as a pair. And then, so you would want the embedding of the question to be close to its correct passage, and you want it to be far from random passage. Right? And then maybe the most famous example nowadays is CLIP. I'm sure if all of you have seen this picture where, this is truly multimodal in the sense that they are actually, the inputs are, one is text, one is, one is images, and, we encode them. And so each one has its own encoder. And the way the loss works is you want the embedding of the image to be close to its own text, and you want to be far from everybody else by doing, like a softmax loss. All right. Okay. So let's, get some equations in. So we'll be dealing with two versions of this, the single modal and multimodal. Single modal is, the InfoNCE loss, and I'll just say what that is. And then multimodal is, a slight variant of this. Okay. So the InfoNCE loss is, what is our data? Our data is pairs of points x and x hat, right? And this is the loss. So you want to minimize over f. Think of f as like a ResNet 18 or ResNet 50 body, right? With no prediction head, so it has a final embedding. So x is, maybe an image, and f is the encoding of the image when you put it through the ResNet body, right? And so you want to minimize, so you want to learn an f to minimize its loss function, which is, has e raised to the embedding of x and the embedding of x hat in the numerator. So you want to bring them closer, and then in the denominator you have an expectation over all other points y of fx and fy, right? And that means you want to keep them far apart. This is InfoNCE, and for the linear case, f is just a times x, and we will be studying the linear case in this talk. Yeah.
Just a clarification. So the EX includes the expectation for x.
Yes, EX is the expectation over x.
And not x.
Oh yeah, so x and x hat. Yeah, it's with the joint distribution. Yeah. Okay. I should have said x1 and x2, and then x is like the vector x and x. But it's an expectation over x and x hat. Every x has its like pair. Okay. Okay. And then what is the multimodal version of this? It looks pretty similar, except now we have two encoders. We have an FV and an FT. And the first term is, okay, so here the partner is in a different modality, right? Like previously in InfoNCE, the partner was the same modality because you just like took a mirror image of the image and so on. Now the partner is in a different modality. It's a piece of text and my partner is like an image in somewhere else, right? And so I want a loss to make the image encoding, V is like vision and T is text. So I want my image encoding to be close to my text encoding for the pair. And I want it to be far away from other text encoding. So this is equivalent to taking a softmax along the row for that on that clip matrix. And then you also take a softmax along every column. And that's the second thing where the numerator is the same. But in the denominator, now you have that your particular piece of text should be far from all images. So here is kind of cross modality, and you have two different encoders. And we'll again be looking at the linear case where you just have a matrix AT, which takes your XT to a lower dimensional space, and you have XV for AV for XV. Okay, so first let's look at yeah. So all right, yeah. So this was some brief background on contrastive learning or contrastive losses. And the question you want to answer is that, this is a pretty simple idea, right? Like, you have a point, you have some partner that we can kind of legitimately think is a good partner. And all you need to do is you need to bring it closer to its partner and far away from everybody else. And it's like a very powerful, and that simple trick gives you a very powerful model, right? And so the question is why? Right? Like, why does this do this? And can we theoretically understand why it's doing that? Right? What is so special about these like partner points? Right? I mean, at a high level, they are semantically related. Okay, fine. But can you say a little bit more? Can you capture that notion a little bit statistically? Right? So that was our motivation. And so, to get some insight, we studied in a very simple context, which is linear representation learning, or it used to be called dimensionality reduction, but now people call it representation learning. So linear representation learning for Gaussian mixture models. Right? And so, okay, so I'll do this, and the talk has two parts. The first one is just InfoNCE for Gaussian mixture models, and the other one is like a multimodal Gaussian mixture model for clip style losses. Yeah.
So what we in terms of like you're learning the linear one, so that is very similar to what triplet-based metric learning does as well, right? Like in the sense that the loss is a little different in the sense instead of it being usually in the expectation, in the denominator there is a kind of integrating over all points. So in the triplet one, you are taking literally 3, so the denominator would just have the 2 things, right? So
we'll just have one
here.
Yeah.
So in terms of like statistically, how much difference would that make in terms of like we understand like sample complexity for metric learning, and compared to that, how much would the so what does it qualitatively separates the that framework?
Yeah. So typically, okay. So let me rephrase that question, right? So what metric learning is that you have, the y's are the negatives, right? And so what metric learning is that for every point we have one positive and one negative, right? And what this is that you have a lot of negatives, right? And so what is typically seen in contrastive learning is that, like you don't actually take an expectation of the negatives of the full data set, right? You have like a batch, and then you do in batch negatives. And the quality of the representations depends very much on the size of the batch. You do need large batches for contrastive learning to work well in practice, right? So, okay, so that's the in practice answer to your question, right? Now, in the context of like, simple statistical models, I'm not sure what the answer would be. Like, maybe this is simple enough so that it doesn't matter, right? But in practice, definitely you want lots of negatives. Yes.
You said what makes a good partner, but there's also the role of the negatives, right? We talk about part negatives. We also talk about the
No, I will. Yeah. So this is a great question, right? Which is that can you just do in batch negative? Okay. So naive contrastive learning is just in batch negatives with some random batch, but you can do hard negatives. That's a great research direction. We are not going to talk about that, but maybe we can try to understand that in this like simple baby context that I'm going to talk about. But yeah, I'm not going to talk about hard negatives, but it's an important area, I think. Okay, right. Yeah, so this is what our talk is going to be about. We're going to study a contrast learning in a very simple context, which is a Gaussian mixture model, right? Either multimodal or single modal, right? Depending on the kind of loss you want to look at. Okay, So first, let's look at a single mode with InfoNCE laws. Okay, so just some brief background, mainly for notation, right? So what is a Gaussian mixture model? So let's say we have like uppercase K, a number of components, and the kth component has a probability WK of, and it's a Gaussian with a mean mu K and its covariance sigma K. So you have like uppercase K Gaussians, and each of them has a certain associated probability. And the way you generate, so what this kind of notation means is the way you generate a point is that you first, flip a K-sided dice with probabilities WK, and then you generate a point from that Gaussian, and then you keep doing that every time. Okay. Some special cases. Oops. If you have, if all the covariances are identity, or maybe scaled identities, then these will be like spherical Gaussian mixture models. And on the other hand, if all of them have the same sigma but it's not identity, then it's a shared covariance Gaussian mixture. And so kind of two special cases of GMM. Okay, so what does linear representations for GMMs mean? So the task is we want to find a projection, right? We want to find projection A. Which takes it from the higher dimensional space D, where the points exist, to a lower dimensional R, right? And we want to find it so that the projected components are better separated in the projected space, right? So there are the components in the ambient space, and when you project them into the projected space, they should be like better separated, right? And we will see what better separated means. But intuitively, you can imagine it's like the distance between the means as compared to the sizes of the covariances after projection. And typically, this is done so that subsequent tasks, like, for example, k-means clustering or nearest neighbors, classification, blah, blah, all this can be done in lower dimensional space and often with better accuracy. Right? So it's pretty popular. And you can think of it as like a rudimentary form of representation, right? Like you're taking it from a high dimensional space to a lower dimensional space, in this case, only by a linear. So the classical approach is to take the top R SVD subspace of the data matrix. Right, you take XX transpose, you sum it up over your data, you have a matrix, you take its top, eigenvectors, I guess, because it's symmetric, and then you project everything down to the top eigenvectors. Okay, so and this often works very well if you have isotropic clusters, right? So this is an example where I started with 2 clusters in 50-dimensional space, and if I take and then I projected down into like 2-dimensional space. If I take a random 2-dimensional space, then the blue and red points are basically right on top of each other, right? There's no way to separate them. This is a really bad projection if you want to do anything downstream. While if you take the first 2 singular vectors and you project onto that 2-dimensional space, then they are pretty well separated. This is the same 50-dimensional Gaussian with 2 different projections. So this is some very classical like Kanan-Vampala style stuff, right? I'm just giving a like brief recap. Okay, so when does this work well? So the SSVD is like the SVD based subspace, right? If you have spherical Gaussians, it works really well, right? On the other hand, and this is again from I think I think this is from Kanan-Vampala, one of Vampala's papers, the parallel pancake example. Okay, so so if I have 2 Gaussians in high dimension, let's say in this case 2-dimensional space, which are like pancakes in the sense that they have very high variance in one direction or in the same direction, and very low variance in the direction that separates their means. Right? These are visually pretty well separated Gaussians. Maybe even better separated than those Gaussians. But when you do an SVD-based projection, you actually screw it up, right? Because the SVD learns that subspace, right, of the shared covariance. So the moment you go out of spherical to even shared covariance matrices, you have these issues, right? And SVD-based methods work really poor. And kind of the reason is that like you can rewrite that the SVD-based objective is basically this objective, where you want to maximize over projection matrices A of kind of the trace of A transpose times this thing, which is the covariance plus the means of every point, and then you're adding it all up. And so if you have a a sigma k which has a big nonsense direction, it can significantly screw you up. So this is linear representation learning for Gaussian mixtures. Using an existing method, it has this issue when you have a shared covariance matrix, which is you may not get like a good subspace. Maybe you get a much worse subspace than not doing anything. Okay, so what does contrastive learning do here? And what even is contrastive learning for Gaussian mixtures, right? So, okay, before we go there, one more thing. How do I determine the quality of a subspace, right? I mean, the theme is like quote unquote contrastive learning is going to get you a better subspace than SVD, okay? I mean, I'm sure that's pretty clear to you by now that that's where I'm going. But what does it mean to be good? So, standard metric for good is the Fisher discriminant, right? So if I have any subspace A, then the Fisher discriminant is the trace of this product of matrices, or the first matrix is inverted. So this is the intercluster covariance, right? And this is the across cluster covariance. So yeah, I mean, if the mu's are really far apart, this will be pretty big. And if the mu's are closer, I mean, sorry, the projected mu's, then, and if the projected mu's are closer, this will be small. And kind of vice versa. So, you have this like intercluster covariance inverse times the across cluster covariance. And this is the Fisher discriminant in this side. Okay, so we want, and so, we want to find an A that has a really, good J. Okay. All right. So, if you have a shared covariance matrix, you actually don't need shared. Like, if a sigma bar is the kind of ensemble covariance matrix, then the best Fisher subspace is the span of a sigma bar inverse times each of the mu's. Right? You take the span of that, and that's the best subspace for Fisher. Right? And so in the parallel pancake example, this is SV. Like if the two pancakes are exactly lined up in the sense that in this sense where the bad direction is orthogonal to the direction between the mu's, then the Fisher discriminant is the optimal subspace. Right? So like S mu is the direction that goes through the centers. If you have the parallel pancakes split a little up and down, SVD is still kind of pretty bad. It's still this one. S mu, which goes between the centers, is actually not as good as SI. Yes.
Yeah, so I guess when you say that SVD is not good, but what if you put a few more eigenvectors in this case?
Yeah, it won't help. No, it will not help. Yeah, because the moment, I mean, like the fact that you keep the first eigenvector means you have captured a lot of that overlap. You really don't want this first vector at all. Yeah, so more eigenvectors won't solve it, right? And I mean, like in the most optimistic case, you keep enough eigenvectors and then you have like as much separation as you had in the ambient space. But you cannot become better than ambient with more eigenvectors. In this parallel pancake example. Yeah.
Also, good question on the metric K. Like, is there a range that it's between?
No, it may not be between 0 and 1. Yeah, I mean, it's just given the mu's and the sigmas, it can be, something. Right?
When I'm reading J is the higher the better, right?
Higher the better. Yes. Yeah, no, but I mean, there's no I guess what he's asking, is there a generic scale, like is the best J always 1 and the worst is 0? And no, not really. I mean, it depends on the muse. That is.
I mean, the scaling of the A is clearly.
A is a projection matrix. Yeah. Yeah, A is a projection matrix, but if sigmas are really big, then you have a big matrix. Okay. So this is, this is like Fisher subspace. Fisher subspace is nice. We want to get Fisher subspace. Right? That would be nice. SVD does not give you Fisher subspace. Okay, based on these examples. SVD does give you the Fisher subspace if you have isotropic Gaussians, right? Like if you have, basically your Gaussians look like, balls, spherically symmetric balls, even of different sizes, it's all good. But otherwise, no. Okay, so we want to study contrastive learning. What is missing? We need a notion of augmentation, right? Like, you know, we just have like Gaussian mixture. There's no notion of augmentation, right? But we need a notion of augmentation for understanding contrastive learning. Okay, doesn't already exist. So we'll just make up one. Okay, and so I'll just say right away that our results, whatever we do here, is not comparable to actually learning mixtures of Gaussians, right? Because we have augmentations, and actual learning a mixture of Gaussians has no augmentation, right? Our objective is not to, you know, better solve mixtures of Gaussians, but it is to understand contrastive learning. Okay. So we need to define a new distribution of points, right? This is our, like, you know, this is how we apply contrastive learning to Gaussian distribution. So contrastive learning needs pairs of points. I need these pairs of points to come from some mixture model, right? So I've given a mixture model, right? And so that's a distribution for a single point, but now I want to have a joint distribution for pairs of points, right? And the joint distribution is this, right? So first I flip a coin with probability 1 minus delta. The pairs are just independent draws from the same Gaussian, right? So the first point is this, and the second point is this. That's what this product means. Okay, like this is the distribution of the first point, this is the distribution of the second point, and it's just a product distribution. Yes.
Sorry, this is super cool. Just to confirm, in this case, we like know, we assume we know the Gauss, like the underlying Gauss. Right?
This is just a generative model for the data.
Okay.
Yeah, but in our algorithm, we have to find a good A without knowing the mu's and sigmas.
Gotcha. Thank you.
Yeah. Okay. Yeah. So with probability 1 minus delta, we did, you know, the 2 points are just 2 independent draws from the overall mixture distribution, right? So when delta is equal to 0, we just have the original Gaussian mixture. Okay. And with probability delta, both points are from the same component of the Gaussian. So with some probability, they're from the same component, which means you're getting like extra information about the Gaussian. I know, like about the mixture model. Right? You're getting a little bit of information. You're getting 2 points, which I guarantee come from the same Gaussian. Same little component within the GMF. So that's with probability delta. So kind of the value of delta is like the strength of the augmentation. Right? If you have like, you know, delta is high, the augmentations are very strong, right? But these are 2 independent draws from the same Gauss. So it's still a product distribution, but within a single Gauss. Any questions? Yes.
Are you going to use the knowledge of the Gaussian components to create the pairs, augmentation pairs, or you're agnostic to the knowledge?
Right. So I'm agnostic to how the pairs come about. This is what I assume about the pairs, right? Like what actually happens in practice is that people do cropping of images and so on, right? And we want to kind of statistically capture that notion, right? And so, you know, the way we statistically capture it is we assume that we are given pairs of points. Like, okay, so let me step back. The data for a standard Gaussian mixture is I have a bunch of points, find me the components. Our data is I have pairs of points, find me the Gaussian mixture. And for every pair is generated in this way. That is my machine learning problem.
So in this model, we should think of delta as large, or
delta is between 0 and 1, and it's like the strength.
Typically think of it as large. Like this is the chance that your pair correctly match points from the same cluster. Right?
Yeah.
So I should think delta is large in practice.
Yeah, I mean our theorem will have delta in there, so you can see like, you know, yeah.
But here we don't know if
We don't know what delta is a priori. Sorry?
We don't know which is that.
Right. Yeah. Okay. Yeah. So that's a good point. The pairs are not labeled as like good pairs and bad pairs. I don't know, you know, like for every pair, it's a pair. I don't know if it comes from the same Gaussian or not. Yeah, thanks. That's a good clarification. Yes. Okay. Any questions? Okay. So I think this is the main thing to to understand that, you know, we need a notion of augmentation, right? And in the case of Gaussian mixtures, we can have this notion of augmentation. We're thinking of some other statistical setting. you might need your own, definition of an augmentation. Okay. All right. So with that, we have the theorem, and basically what I'll say what the theorem says in a minute, but essentially the punchline is that if you do the InfoNCE loss, or the linear version of it, which I had mentioned in a few slides before, in the population setting, right, it leads to embeddings of points that lie exactly in the Fisher subspace for shared covariance, right? When delta is equal to 1. And when delta is not 1, it's kind of an approximation of the Fisher subspace. Okay, so let's see exactly what the theorem says. So suppose we have a Gaussian mixture model with shared covariance, so the sigma doesn't depend on the k, right? And based on this, we get pairs of points using f hat, which is this like weird product distribute, delta time product distribution that I just mentioned in the last slide, right? So f hat is this augmentation distribution. We get points from that, and then we do InfoNCE loss, right? So this is, let's say, this is the InfoNCE loss, and then we get A star. Then okay, so A star is what the InfoNCE loss gives you. And let SF be the Fisher optimal subspace, right? So it's like the sigma inverse span, a span of sigma inverse mu's, right? So then what this says is that, when you have enough rank, when R is bigger than K, then the column space of A star, your projection matrix, will be contained inside the Fisher. So we will not learn any nonsense directions. If we have perfect augmentations, which means that every pair is guaranteed to be from exactly the same component, then your projection will be exactly the Fisher optimal subspace. Yes.
In the Fisher subspace, is there a notion that one direction is more valuable than another?
We are just going to project onto the entire Fisher subspace, or the minimal Fisher subspace.
Right, so my question is, when we get only subsets, like a subspace in the Fisher space, do we get only the most valuable subspace, or do we just get some?
Yes, the Fisher subspace is the most valuable subspace. So like if you go back here,
right, if it has two directions,
where did it go?
would one of them capture more information than another? I guess is my question.
Maybe it will, maybe it won't, but we will just project onto everything. But yeah, okay, I was trying to find it. Yeah. So I think not all of these directions are created equal.
Okay.
Right. So if you had to go less than K, then some are better than the other. But we are in the regime where our projection is bigger than K. Right. So we're going to capture, hopefully we capture the entire Fisher subspace. And we don't capture, the main thing is we don't want to capture bad directions. And so that's what the theorem says. We don't capture bad directions.
Okay, then I guess you just answered, but you're not guaranteed that A has rank. Anything, right? It could be rank 0.
Right. So if we have perfect augmentations, then it's the rank of the Fisher subspace. And if you don't have rank 0, then it's a subspace. Then it's a subset of it. I find it hard to believe it will be rank 0, but yeah, that's actually this is
Does it agree, Grace? Like if delta is 0.9, can I prove that it at least has a constant fraction of the rank or something? Maybe.
Let's do it. Yeah. So we don't even have a counter example that if delta is less than 1, this is not true. It's just that the proof kind of doesn't.
Yeah. So you describe the distribution for the pairs. So typically will be from the same. How do you get the negatives?
The negative is just like everything in the batch. So it's just like, yeah. So, in the population case, it's just the expectation over, well, no, this is a clip. It is just that Y is just like from the entire GMM. Yeah. Which is how contrastive learning is also done, right? Like you just imagine this is the infinite batch setting of contrastive learning. Okay. Yeah. So this is the result we have so far. We don't actually have a counterexample. I personally think that this should remain true, even if delta is less than 1, but we don't know. Yes.
No dependence on sigma.
This is all population. So there is no dependence on sigma now. There is shared covariance. Everybody has sigma, right? So we are in this pancake style setting, but
essentially like the A star that was recovered, suppose if sigmas were all identical, then the
Can be the span of the muse. Right? Because the Fisher subspace is sigma inverse muse, right? So if sigma's identity is just the span of the muse. But if it's identity, even like PCA or whatever, like SVD based subspaces.
yeah, so yeah, that's what I was getting at. Like, depending on sigma, like
The space you learn will be different.
will be better than the one that you learned.
Yes. Yes. Yeah. The whole point is that even if you have a bad sigma with like really bad components, which if you just took SVD will, screw you up, it does not screw up contrastive learning. Once you have these like, once every point has a friend, the friend can help it like, not be screwed up by a bad projection.
Is there a certain requirement for how much data we need to contrastively learn to be able to recover this Fisher subspace?
Not in our results. I think we can extend it. But we haven't done that yet. But like as I was, I think that's the same question before. I think operationally for like actual large model training, it's very important to have big batches. Yeah, like the bigger the batch, the better. Like if you train a clip model with like I think the clip paper, even VIT base has 32K samples per batch. So which means you have 32K negatives for every positive. Yeah, and I think, and we have trained with like batch size of 128 and clip is like really bad. So it matters, even though it's technically the same loss. Okay, multimodal, right? So slightly different assumption. So remember what is multimodal? So we have two modalities now. We have like XVs, which are in some dimensional space, and then XTs, which is like in another dimensional space, right? And think of it as like images and text, but we'll of course have just vectors, and we are doing linear dimensionality reduction, right? So what is my notion of partners for multimodal? So it's just this, right? Like so now I need to define like a generative distribution for like pairs of points, where I have a Gaussian mixture in one modality and I have another Gaussian mixture in a different modality, right? And so what that is that I'm going to pair the Gaussians, right? So one component for me now is one Gaussian in the space of images and another Gaussian in the space of text. That together makes one component, right? It has kind of two versions, right? The image version and the text version, and then another component is a different Gaussian in image space and a different Gaussian in text space, right? So yes, give me 1 minute. So I have like a dv dimensional Gaussian whose mu is mu vk for the kth component and covariance sigma vk, and then there are k of them, and each of them has a like a weird twin in another space, which is in the dt space, where mean is mu tk and the covariance is sigma tk. Right? And then the way I pick pairs is I first pick the component, and then I pick generate a point from each side of that component. Yes. 3 minutes left. Okay. Yes. I just started part 2. No, the part 2 is very small. Yeah, I've already made up a lot of any other. Okay. Yeah. So yeah.
So you assume within each component, these two modalities are independent, and that their interaction is only through the mixture.
It's only through the mixture, exactly, right? So and this is how a clip data set is, right? Like you have image and its caption, image and its caption, and there's no real interaction between the images. Okay, so here we don't need any weird notion of augmentation coming from same component, none of that, right? The pair is just from a different modality. There is no delta, none of that. Okay, yeah, and so we just draw pairs from these components, and now given this assumption, we can look at the clip contrastive loss, which had those two terms in the linear case setting, right? And then the theorem is that if we have this clip contrastive loss that I mentioned before, and then I optimize it, and I get AV star and AT star, then a similar thing holds to what we had before, but in each modality, which is that the column space of the projection is within the optimal subspace of each modality separately. So now I have like two Gaussians, right? Like I have Gaussian in the space of images, I have Gaussian in the space of text, and each one has its own Fisher subspace, which may have nothing to do with each other, right? But so why I find this interesting is that, you know, we just enforce cross-modality correspondence, right? We didn't have this weird notion of augmentations. Just cross-modality correspondence is all you need to find this Fisher subspace in each modality.
Find the CCA subspace then?
Sorry?
Find the CCA subspace across two views.
I don't know what the CCA subspace is for cross modality. It finds the Fisher subspace within each modality.
And have two different views of the data.
Two different views of the data.
So there should be some subspace that maximizes the correlations.
Okay, we have to be a little bit careful about what we mean by two different views of the data. It's not like there is some super high dimensional Gaussian and you know the XV is like one kind of projection of it and XT is another. It's not that, right? Like
I guess here what happens is that the feed perspective is not really a correlative.
yeah, it's not.
It is not a linear correlation.
Right. Yeah, there is no within component loss.
I know, but you could, you were just trying to do Gaussian mixture. You could take these two views of the data and look for them.
Yeah, but they may not be two views of the same underlying Gaussian. I don't think that is true because I don't assume anything about the relative locations of the mu's, right? Like, you know, in my image space, like mu1, mu2, mu3 may be in a line with mu2 in the middle, but in the other space, it may be mu1, mu2, mu3 with like 3 in the middle. And then that's not a two views of the same space.
I mean, they would have separate subspaces for the two views, but there's some common.
I'll have to find out more from them. Yeah. Okay, anyway, but yes.
The views are different, or could it?
The mu's are all different. Yeah, the mu's are all different, and the sigmas are also all different. Oh, okay, sorry. In the general model, but in our theorem, they have to be shared covariances, right? So the covariance has to be shared in each modality, but they can be different across modalities. The mu's are all different no matter what, but the covariance within each modality has to be the same.
So do we think that there's like, are we assuming that there's some transformation from the view in one space to the view in the other, or like that's not it?
That is this transformation, AV and AT. Right?
Oh.
So AV is mapping images or whatever to our dimensional space, and AT is measuring, like, you know, projecting text onto the same R dimensional space.
Right. I mean, I guess projecting image onto the text space.
No, onto some other third space.
Okay.
Both are being mapped to a third space, which is neither text nor image.
Okay.
Okay, so I'll finish. I think I'm already over time. So we do have a simple setting to understand why contrastive losses work, and which was linear representation for Gaussian mixtures in single and multiple modalities. And for, you know, we need a new notion of what it means to be a partner point for contrastive learning. What I'm really interested in is to see if we did all this, right? But nobody cares about like linear representation learning, right? But we want to use this hopefully to understand, can we develop a better contrastive loss, right? Like I think this would be very interesting. And you know, maybe in some settings, if not the most general one. And then the second one is to extend this analysis to one hidden layer nonlinear networks, because I think if you do one hidden layer, you don't need to have this like shared covariance assumption. It can be like general. I feel if they are well separated, right, then any linear projection won't do the job, but nonlinear projection, even a single hidden layer nonlinear projection might do the job. That's it.
Let's have time for one quick question before the break.
We had many questions.
Yeah, I guess we had a lot of questions already. All right, let's take a break before. So what time should we start up?
I would say let's take like 10 to 15 minutes.
So yeah, be back here by like 11.